Most of the reactions we've looked at so far have involved transferring of an atom or a group of atoms from one species to the other. So in the reaction that's shown right there, acetic acid, which gets the symbol HOAC, acetic acid reacts with water to make the acetate ion and hydronium. This is a reaction we looked at in chapter 14 quite a bit. It's a weak acid, you've got some hydronium, etc., etc. However, the important part for us right now is that the hydrogen from acetic acid is being transferred to the water. It makes hydronium and then also the acetate ion. And most of the reactions we've looked at up till this point have been this way. But in this chapter, we're going to look at what's called electron transfer. And in electron transfer, you may not see the atoms change at all, like in this example right here. In this reaction, copper metal, which is copper solid, reacts with two silver plus ions, which are dissolved in water, to make copper 2 plus ions, aqueous, and two silver metal atoms, two silver solids. And that's what we're going to focus on here. Now notice that copper and silver aren't coming together, transferring stuff like that, but copper is going to copper 2 plus, so copper solid, copper with as a metal, is going from a 0 charge to a positive 2 charge, and that can only happen if copper has lost electrons. Remember, electrons are negative, so the copper 2 plus is more positive than the copper. That means the copper metal has lost electrons, becoming more positive. But likewise, the silver plus becomes silver 0 as silver metal, so the silver plus has to gain electrons in order to become silver metal. So you can see the electrons here are being transferred essentially from the copper to the silver plus. And in the process, you end up with copper, which is more positive, copper 2 plus, and silver, which is less positive, i.e. silver 0 or silver metal in this case. So these are going to be the kind of reactions we're going to look at in this chapter. You can break the copper-silver reaction down into what's called a half reaction. And in a half reaction, you're allowed as a chemist to show electrons. Now, you don't normally show electrons as a chemist. You try and keep those hidden away. But in electrochemistry, it can be super helpful to write these reactions as half reactions. So to write a half reaction, you want to put, for example, the copper species together, and you want to put the silver species together. Put the species which are somewhat similar to each other together. So in this part then, you'd have copper going to copper 2 plus, and again, copper can only become more positive if it loses electrons. So to become a positive 2, that means it has to lose 2 electrons. So you could write this as copper going to copper 2 plus and 2 electrons. And with the silver, you can do similar process. You can take the silver plus and make silver metal on the product side. That can only happen if the silver plus gains an electron. Now, because there are 2 silver pluses and 2 silver metals, we can write 2 silver plus 2 electrons makes 2 silver metals. So these would be the half reactions for this particular process. Now, the note at the bottom is important. I think all of you at this point are really good about having a balanced reaction. So the atoms on the left equal the atoms on the right, the reactant atoms equal product atoms, all that kind of jazz. But it's also important to realize that these reactions should be balanced for charge as well. And all of the reactions on this page follow this process. So if you look at the main reaction right there, which is copper and 2 silver plus going to copper 2 plus 2 silvers, on the reactant side, copper solid, copper metal doesn't have a charge of 0, and the silvers, there's 2 of them, 2 times positive 1. That means the whole reactant side has a positive 2 charge. On the product side, the copper 2 plus has a positive 2 charge, and the 2 silver metals have no charge. So you've got a positive 2 on the reactant side and a positive 2 on the product side as well. This reaction is balanced for charge and mass, and you can do that for any of the reactions we're looking at on this page or any of the reactions we've looked at in general. We haven't dealt with the charge so much because it hasn't been as important, but in this chapter it will. Keep that in the back of your mind. All of the reactions should be balanced for charge and mass both. When you have electrons being transferred in a chemical reaction, they're referred to as oxidation reduction or redox reactions. And we looked at redox reactions back in Chem 221 briefly, but we're going to do a better job right now. So these redox reactions can result in the generation of an electric current, like it's going from some chemical species which is creating the electrons to the species which is accepting the electrons. And along the way, you're going to have moving electrons. Moving electrons is essentially what electric current is. So this field is often called electrochemistry. It's using chemicals in order to enact chemical change through electrons being transferred, and it is a type of system. Now, a battery is essentially electrochemistry. It's basically two chemical parts. One part is creating the electrons, and the other part is accepting the electrons. And if you can control this, you can control the battery, which of course is so important for our lives. When you talk about redox reaction, you must know these terms. The two most important parts probably are oxidation and reduction. So an oxidation means that electrons are being lost, and reduction means the electrons are being gained. And oxidation and reduction are usually relative to the reactants, not the products. We'll talk about that. Now, as a species loses electrons and is oxidized, you see an increase in the oxidation number, or the charge on the metal. We'll come back to this in a little bit. And likewise, reduction, when you gain electrons, you're going to have more negative charges added in, so the oxidation numbers will decrease, become more negative, if you will. And if that wasn't enough, oxidizing agent is another term for something that's reduced. And reducing agent is another term for something that's been oxidized. And I am just perplexed that these kind of definitions exist. Apparently, the idea is that an oxidizing agent is a chemical that allows another species to be oxidized while it itself is reduced. And reducing agent, same thing. It's allowing something else to be reduced while it itself is oxidized. And again, I have no idea why these definitions were created. I am just the messenger here. I did not create these rules. But anyway, keep that in the back of your mind. Have I introduced you to my friend Leo the lion? And Leo the lion says, "Grr!" And no, your instructor has not completely lost it, probably partially, but not completely anyway. This is an acronym. Leo says GER. Leo stands for lose electrons oxidized, and GER stands for gain electrons reduced. So if you look on the zinc and the copper 2+ there on the middle left, zinc is losing 2 electrons to become zinc 2+, so zinc is being oxidized. We would call zinc the reducing agent here because it's allowing other things to be reduced while it itself is oxidized. And likewise, copper 2+ is gaining electrons to become copper metal. Copper 2+ is being reduced. We would say that copper 2+ is the oxidizing agent here. Copper 2+ is being reduced, and it's allowing something else to be oxidized. Leo the lion says GER is my favorite expression, but you can also use things like oil rig. Oxidation is losing, reduction is gaining. You can use any of these kind of acronyms you want, but you need to know when something is oxidized and reduced, and likewise reducing agent, oxidizing agent. If you have a cooler saying than oil rig or Leo says GER, let me know. But I'll be referring back to Leo the lion says GER just as we go through this section. Here's a question you might see. Which species is being oxidized in the following reaction? And you can see there's nickel, silver plus, nickel 2+, and silver metal. And then it says not a redox reaction. So let's start with the easiest one. Notice how nickel is becoming more positive on the product side, nickel 0 to nickel 2+. And notice how silver plus is going to silver. So it's going to a less positive state. So one part is being more positive, one part is becoming more negative. This is definitely a redox reaction. So answer E is out. The other thing about oxidized and reduced is they always refer to reactants. It won't refer to products. So if the answers, E is not right. Silver and nickel 2+ are both products. So that's not going to be correct either. It's going to be nickel or silver plus. Now, oxidized is the Leo in Leo says GER. Oxidized is lose electrons oxidized. So you want something that has lost electrons. And remembering that electrons are negative, that means you want something that's more positive. So if you look at this reaction, nickel going to nickel 2+, nickel is becoming more positive. Nickel can only go to 2+ if it's lost 2 electrons. Likewise, silver plus here is going to silver 0. So silver plus is becoming less positive, more negative. Silver plus is going to be gaining electrons. So here, because nickel's becoming more positive, it is losing electrons. Nickel is being oxidized. Silver plus is gaining those electrons to become silver metal. It's becoming less positive, more negative, all right? That's why it is being reduced. And in a redox reaction, you always have to have something being oxidized and something being reduced, unless they're half reactions, but most of the time people talk about the full reaction, and then you will have something oxidized and something reduced.